Take a look at worksheet number 3 that we had for homework, specifically the second graph that we have, starting at question number 7. This says we got a position time graph with position on the y-axis and time on the x-axis. You know that the variable that appears first in the title always appears on the y-axis of the graph. What variable is that? Is that a manipulated or a responding variable? The one that appears first in our title, the one that appears on our y-axis of our graph. Yep, Marty? Yeah, that's your responding variable. That's the one that changes in response to the manipulated variable, which appears on the x-axis. Sometimes we look at time and think, how can time be a manipulated variable? We're not changing the time. No, we're not changing the time, but it's because the time changes that the position changes, right? Your position doesn't change if your time isn't changing. So your position changes still in response to the time, even though it's not us directly manipulating the time. All right, so you see 2 lines here. We'll call it phase 1, and we'll call it phase 2. Phase 1 goes from 0 to 10 seconds. Phase 2 goes from 10 seconds to, what is that, 13 seconds? What's going on in phase 1? Tell me what's happening, Marshall, in phase 1. No, not deceleration. Straight line always means what word? Constant or uniform, yes. Now, if it's a position time graph, it's a uniform or a constant what? Yeah, uniform motion, you could say, which is the same as saying constant velocity, right? Constant velocity. But in this case, because it slopes downward, that would be a constant negative velocity. You got your car in reverse, right? And driving backwards? Not necessarily. You're driving backwards. You're going in the negative direction, but your car doesn't have to be in reverse. You don't have to be walking backwards. You're just walking in the negative direction, that's all, or driving in the negative direction. What about the second phase there? What's going on there? That's a constant velocity as well, right? Because it's a straight line on a position time graph. But specifically, we'd say this is a constant positive velocity. In other words, it's going at the constant speed forward in the positive direction. All right, let's take a look at question number 7. Calculate the displacement of the object between 0 and 10 seconds. Displacement is defined as change in position, right? So if we're going to find the change in position, we need 2 positions and then subtract them, right? How do we get position on a position time graph? Up and over, good. So we're going to go up and over twice. Well, kind of. There's not really over to go in the first one for the initial, right? We're just going up, and it's like, oh, the initial position is 14. The final position at 10 seconds is 0. So we're going to say the displacement, the change in position, is 0 minus 14, which is negative 14 meters. How many people got negative 14 meters there? Be careful there. It's not 14 meters, right? Okay, 14 meters would get you half marks for this. Okay, it's not 0 if you said 14, but it doesn't give you full marks because it should be in the negative direction. Now, having said that, look at what we've done on the y-axis. That's west, right? Negative 14 meters means what? East. It makes sense for us on a graph to define whatever they have on the y-axis as our positive. So positive is west, therefore negative is east. If you happened to have defined it the other way, I wouldn't do that. But if you did happen to do that, then you should have gotten a positive 14. Or you could have said alternatively, 14 meters to the, no. You could have said 14 meters to the east, right? 14 meters to the east would be your answer. I just leave it as negative 14, though, to be honest. Okay, next one, calculate the displacement between 10 and 18 seconds. Same method here. Final position looks like 6. Initial position is 0. We're going to say 6 minus 0 is 6 meters. By the way, we don't worry about significant figures with graphs, just whatever. There are rules for that, but we just don't do them. That's positive, which means it's 6 meters to the west. What's the average velocity between 10 and 18 seconds? How do you find velocity on a position time graph? Yep. Yeah, it's displacement over time, which is the same thing as saying the one word. The slope. Yeah, the slope of the graph. So rise over run, delta y over delta x, y2 minus y1 over x2 minus x1, or you can just say displacement over time. They all mean the same thing. I like doing displacement over time for my slope. We already found the displacement at 6.0 meters, and the time is 8.0 seconds, and that gives me, what, 0.75, I think? And number 10 says, what's the average velocity between 0 and 18 seconds? I got a couple of options here. Between 0 and 18 seconds, you could draw a line, a straight line, 0 to 18 seconds. It's not really going at a constant speed there, right? But remember what we said for v equals d over t? It's constant or average, and that v equals d over t really represents the slope of an average line here, our green line. So you could draw that green line from start to finish and find the slope of it. Or, alternatively, you could just say, well, the average velocity from start to finish is the displacement from start to finish over the time. The displacement from 0 to 18 seconds would be what? What is it? -8, you say? We're going to say it's, what, 6 minus 14, final minus initial? It would be -8, you're right. And my time here is 18, so we're going to say that's, what, -8 meters over 18 seconds, which is 4 over 9, which is -0.44 meters per second. So 0.44 meters per second to the east, right? Because positive is west, negative is east. Good there? You guys comfortable with that? All right, we got a little bit more to do with this whole position time graph stuff, but know that the 2 questions, well, or the 10 questions, I guess, the 2 scenarios that you've just seen yesterday and today, you will get this on your test. Okay, your test is still a ways off here yet. We're not, it's not going to be like, oh, hey, test on Thursday. It's long after the break here, but you know you're going to get one of these questions, okay? For sure. All right, what I want to do right now is take a look at the next example. When I could find it here, here we are. Take a look at the next example, which is a little bit different. Example number 6. I'm going to teach you how to teach you a little trick on your calculators for this one. So it says, use the following information to answer the next question. And the next question says, for this position time graph, draw a trend line on the graph, and then using the stat function on your calculator, determine the average velocity of the object. So this is like, well, this is like data that you would have collected for your lab, right? Except in your lab that you handed in this morning, Google Sheets spat out for you the slope of the graph, which is nice. Back in the day, we'd have to draw a line of best fit and then calculate the slope of that graph. Now it just electronically does it all for me. But what if you got something like this on a test? You don't have Google Sheets at your disposal to do that. So you get a couple of options here, really, but one of them is definitely easier than the other one. And it's definitely more accurate than the other one. The first one is to draw a trend line or a line of best fit and then calculate the slope. Did you guys draw lines of best fit like this in Science 10? Who has drawn trend lines like this in Science 10? Okay, who has not? Okay, about half and half. Okay, no big deal. A trend line or a line of best fit simply is a line that represents the trend that's happening. It represents the trend that's exhibited by the graph. You can see that this looks like it should be probably a straight line, right? Or close to a straight line. So let's draw a straight line that kind of goes right up the middle of these points. Straight line with a ruler or a straight edge, the edge of your calculator or whatever the case may be, that goes right up the middle of these data points. My straight line might look something like this. Kind of hard to do it on here, so bear with me. That's not bad, actually. Right up the middle, just like this. Take a straight edge. Everybody do this. Take a straight edge, whether it's your calculator or a protractor or whatever. If you don't have a straight edge, let me know and I'll give you one. And draw a trend line. You should have a couple points above, a couple points below. This would be a terrible trend line. Because that doesn't represent the trend that's happening at all, does it? That doesn't follow the trend. This would be a terrible trend line. It's better because it's closer to what the trend actually is, but it's still not very good. The one that I have drawn there in black is quite good. The beauty of the technique that I want to show you is that your trend line doesn't actually have to be perfect. In the old days, we had to draw our trend line really, really, really good because we would take 2 points on the line and then calculate the slope of that line. So if our trend line was off a little bit, our answer was, our slope was off a little bit, right? We had to have that trend line perfect. Now, if your trend line is off a little bit, it's not the end of the world because we can determine the slope using our calculators. If you have a TI calculator, that is. If you don't have a TI, I'm not sure if on the Casios or whatever there's a way to do it or not. But you can always go back and pick 2 points and find the slope of the graph, or find the slope of the line that way. So here's what I want you to do. First, we have to identify the ordered pairs here. Well, that doesn't sound easy. Well, it's easier than drawing a perfect line of best fit. So let's identify the ordered pairs of all my data here. We'll do that together here. This looks to be, look at what we're going up by in each line here. 0.4, 0.8, 1.2, 1.6. We're going up by 0.4s. So this is going to be 0.8, and vertically we're going up by 1s. So it looks like 0.8 and 2. Does that make sense? 0.8 on the x-axis, 2 on the y-axis. My second point looks like, what is that? 1.6, 1.7. And what is that on the y-axis? It looks to be about, I don't know, it's hard to tell, 4.1-ish. See that? The beauty of the technique that I'm going to show you here is that if you happen to be off by a tiny little bit on one data point, you called it 4.1 and it was supposed to be 4.2, you'll get away with that. I mean, you don't want to call it 6, but if you're off by a little bit like that, it's not a big deal. Next one is what? What's that, 2.4, 2.8? And what is it vertically? It looks to be about, I don't know, about 5.9. Does that make sense? About 5.9-ish? Again, it doesn't matter if I'm off by a tiny little bit. If you make it 5.1, that's a problem. You make it 5.8, 5.9, it's not a problem. Next we have, what is this? 2.4, 2.8, 3.2, 3.6. What does this look to be? About 3.9? Look to be about 3.9 on the x-axis. And on the y-axis, we've got 5, 6, 7, 8. I don't know. I'm going to call it 8.3. 8.2. Uh-oh, 8.2 or 8.3, which is it? That doesn't matter. Close enough. It's not 8.8, right? Next, what do we got? 4.4, 4.8. It's kind of wacky on this x-axis. We have intervals of 0.4. Usually we see 0.1s or 0.2s, but it's okay as long as you recognize that it's 0.4. On the y-axis here, it looks like we've got, I don't know, it looks like about 9.8, 9.9. I'll call it 9.9. 2 more points. X-axis, what do we got? 5.6. I'll call it 5.7. And 10, 11, 12. I'm going to call it 12.3. Pretty close to halfway between 10 and 15. 12.3, I'll call it. This one is, what, 6.4, 6.8, 7.2 on the y-axis. And we've got, what is that? It's pretty darn close to 14, isn't it? I'll just call it 14. Close enough. Yeah, that seems like a lot of work. But this virtually guarantees you of getting the correct answer for the slope here. You don't have to have your trend line drawn perfectly, although if you do have your trend line drawn perfectly, you should get the same answer. It's just, you don't have to be quite as careful this way. What I want you to do now, guys, is take out your calculators, your TI calculators, and follow along with me. Repeat after me, actually, first. Repeat after me. Stat edit 1. Stat calc 4. Stat edit 1. Stat calc 4. Stat edit 1, stat calc 4. Louder. Stat edit 1, stat calc 4. Got it? All right. So what I want you to do right now is stat on your calculator, edit. That's the first option. 1. Stat edit 1. Press enter. And you should see basically a table that is blank. If it's not blank, let's say you've got numbers on it, then what I want you to do is delete all those numbers. Okay, you want it to be blank. You can delete them, by the way, by going up to the column header, just clicking clear, and then scrolling down. Deletes everything in the column. Because you guys have likely not done this before, you likely don't have anything in there. So now what I want to do is enter all of these coordinates in a table. My x coordinates are 0.8, 1.7, 2.8, 3.9, 4.8, 5.7, 7.2. Those are my x coordinates. Got that? Remember, my ordered pairs are x and comma y, right? So my x axis of a graph would be my x coordinates in the first column of my table. Now I'm going to go up and do the same thing for the y coordinates. 2, 4.1, 5.9, 8.2, 9.9, 12.3, and 14. There we go. Here's my data table. This is what I would put into Google Sheets if I wanted Google Sheets to plot the graph for me. I put it into my calculator because I want my calculator to do the work for me. Now, your calculator is not going to actually plot the graph, but it's going to spit out the statistics of the graph, the slope and the y-intercept, just like Google Sheets does. We don't actually need to plot the graph because it's already plotted for us, right? What do we just do? Stat edit 1. What comes next? Stat calc 4. Stat edit 1. Stat calc 4. Okay, hit stat again. This time, go over to calc and down to option 4. LinReg stands for linear regression. Stat edit 1, stat calc 4. Now I'm going to hit enter on my calculator. Some of you, depending upon your version of the calculator, will need to hit enter twice. Some of you are going to need to hit enter 4 times. Doesn't matter. Just keep hitting enter until you get an answer, okay? Can't go wrong with it. Just keep hitting enter until you get an answer. I'm going to hit enter, 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 enter. I guess it was like 5 or 6 times, whatever. Look at this. Y is equal to ax plus b. A is 1.92. That's the slope of my graph. And the y-intercept of my graph is 0.67. So the slope of this, which is the velocity, right, is 1.92. This would be meters per second. And the y-intercept, which would be your initial position, would be 0.67 meters. It says using the stat function on your calculator to determine the average velocity of the object. The average velocity of the object is the slope of the graph, 1.92 meters per second. That make sense? So the real work is identifying these ordered pairs. If you're lucky, there won't be as many ordered pairs as there are here. There's only going to be maybe 4 or 5 of them instead of, what do we have here, 7. Okay, but in the end, it's just more work. It's not hard, it's just more work. Sometimes what I'll do, just to give you a bit of a break, is actually give you the table that is used to plot the graph. Okay, that's a gift, right? Because if you have the table already, you don't need to identify the ordered pairs then, right? That makes sense? You guys comfortable with that? Okay. I'd like you to take a look at your worksheet then, the one that you were working on yesterday and last night, and take a look at specifically question number 11 on that worksheet. So, exactly the same thing we had here. Draw a trend line, identify the ordered pairs, and then enter it into your calculator. Listen, there's no formal notes for this. What I would do, if I was you writing down notes for this, just write down 6 words. Stat, edit, 1, stat, calc, 4. Stat, edit 1, stat, calc, 4. Okay, let's go to work on this. Let's have a look here now, everyone. I've put the ordered pairs in there already for us, just to make life a little bit easier for us. I'm going to, here, let's go back to the start here. I'm going to go to my data table where I enter my data points. And remember, to get there, it's 3 words: stat, yes, stat, edit 1. Stat, edit 1. Let's enter my x coordinates: 0.8, 1.8, 3.2, 3.9, 4.9, 5.7, and 7.2, or at least pretty much those numbers anyways. If you're off by a tiny little bit, it's okay. Now let's enter my y coordinates. Make sure that the y coordinates go with the x coordinates, so make sure that they match up. 10, 21, 33, 38, is that? Yeah, 38, 52, 60, and the last one is 68. Okay, there you go. There's my data table, my x column and my y column. Now what are my next 3 words? Stat, edit 1, stat, calc 4. Stat, calc, option 4, linear regression. Keep hitting enter as many times as you need to. Calculate. Oh, look at my slope is 9.38. 9, or you can say 9.4. And the units for that would be meters per second. So the slope, 9.4. The velocity is 9.4 meters per second. How many people got 9.4? Good. If you got 9.4, were all your data points exactly what mine were? No, off by a tiny little bit? What'd you still get? So you still got 9.4, right? So it's not 9.38, but it's still rounded to the same thing. Again, we can be off by a tiny little bit with this method and still get the right answer. Good, Marty?
I got 9.48, which I rounded up to 9.5. Would that be incorrect?
No, I'd probably give you that. If I got 9.4 here, I'd probably give you 9.3 or 9.5. Probably not more than that, though, with this method. If you're doing a drawing your trend line and calculating the slope based on the trend line, you could easily be more than that off. Easily be more than that off if your trend line isn't perfect. But with this, you're going to be pretty darn close to 9.4 if you're not exact. Good? Let's try one more example here now. Example number 7 says, use the following information to answer the next question. Again, position time graph. What's the instantaneous velocity at 6 seconds? Instantaneous velocity means velocity at one moment in time, right? Listen, we're not going to go up here and say the position is this value, the time is this, and let's just say v equals d over t. We can't do that because velocity is change in position over change in time. We can't just take one position and one time. It just doesn't work. So what we have to do here is draw what we call a tangent line. And a tangent line is a line that kind of just represents the slope at that specific time. So let's draw a little dot at 6 seconds right here. And then let's draw a tangent line that represents the slope at that specific spot. Let's see if I can do it here. That's not bad. Okay, that's not a bad tangent line. Okay, let me show you a worse tangent line. This would be a worse tangent line. That's terrible. That doesn't show us the trend at all there. What about this one? That's not too bad. Not great, though, because it goes through that point. We don't want it to go through the point. We want it to kind of just skip off the point. It's kind of like skipping a rock on water, right? You skip a rock on water, it just bounces off that one point. That's what we want here as well, is to just kind of bounce off that one point. So let's redraw one again. Oh, that's not good. I tried actually to draw a good one there. It's just hard on the smartboard. You can see that it's not really skipping off that point. It's kind of going along a bunch of data points there on the graph. Let's try again. See if I can do better. That would be good if it was actually touching it. Let me see if I can just move that. There we go. I fixed it. That's a good tangent line. Because that skips off, right? That's skipping your rock right off of one point there. Does that make sense? It's not going into the water. I don't want to draw like this because then your rock is going into the water. I want it to skip off just that one spot on the lake. Now what I got to do is to take 2 points on the graph, I don't know, maybe this point and this point, and find the slope. How do you find the slope? You know this. It's rise over run. Or it's delta y over delta x. Or it's delta d over delta t. You got that?
Yep.
Okay, what I'd like you to do tonight is to try finishing this question, this example yourself, from the point we're at here, knowing that you just have to find the slope of it or delta d over delta t, and we'll check that over tomorrow. All right? Have a good night, everyone.